Welcome everyone, lecture 8.1 on discriminative graphical model. The objective today is to build on the lecture from last week where we talk about the Bayesian network as one type of probabilistic graphical model. Now we'll look at the other family of model based on Markov random fields. These have great advantages. They also allow closer compatibility from an optimization perspective with neural networks, and so they bring some natural building blocks. And we'll look at some architectures building from these conditional random field and then extensions to that. So that's the goal. Before I go in the lecture itself, I just wanted to revisit the last few slides from the last lecture because I had to wrap them up a little bit faster than I wanted. So I'd like to go back to this a few slides and also give a quick summary of the past 7 weeks so that it gives us a nice building block for the rest of the lecture. So I just want to talk about bidirectional and cycle GAN in a little bit more details and going through the slide and giving you a little bit more clarifications. As you remember, some of these generative models, by having this discriminator and generator both working together, if you could say almost competing, that gives very realistic images. I think a great example was this talking head where you have a source face, in this case a painting, and you have on top of that condition, you have some other information, maybe the facial landmarks, and using that source image, the conditional, and then the random vector, then you can generate images, in this case, generating the faces, the talking head. And so one of this type of architecture for that is the InfoGAN as an example for that. In this case, in the InfoGAN, if you remember, the main part of the generative adversarial network is those random variable Z, and that's a random variable, and so the idea is that you could use any of these Z and you should get a synthesized image from the generator. But the key aspect here is that synthesized image will be not compared directly, but the discriminator will have to make a decision if that image is real or not. Is it a real image or is it a synthesized image? The conditional GAN is bring that step further by saying, hey, when you generate, I want to also take into consideration some extra information. Maybe it's a class, like telling you generate an image of a cat, or in the case of the example that I showed earlier, is maybe landmarks. And so these landmarks will be points on the face, and this will be given to you so that the generation of the image takes into consideration those landmarks. The InfoGAN does it in such a way to be sure that the conditional these variables don't get ignored. It makes it such at the end the discriminator also needs to correctly classify if it's a cat, or if it could be also a regression task if it's a landmark. So this is the typical GAN, but I want to talk about two extensions from that. The first extension is to say, I want to train, the main goal of this whole GAN is not to really train a discriminator. The discriminator is just there to help me. The real goal is to train a generator. And this whole framework allows me to train a generator. But maybe I also would like not just to be able to train generator going from my random variable to a synthesized image, but maybe I would like to go the other way around. I would like to be able to train an encoder that takes an image and encode it into a lower dimensional representation. And that's where the bidirectional comes in. And the key aspect that I maybe have glanced over last time is that you will train two things at the same time. You will train both a generator and an encoder, both at the same time. And the interesting part here is for the generator, the input will be some random vector, and then you can synthesize any image from that. And here you will take some real images and encode it. And there, what it is interesting is that the discriminator will have a double task, and find out is it like a real image with real encoding, but in the sense of encoding, a synthesized encoding of a real image, so synthesize encoding and synthesize image, or will it go with a real image and a real random vector? And so it has those double tasks at the same time. And when you do this, that allows you to train not just a generator, but also the encoder at the same time. And as I talked last week, you could also have done that maybe by having an autoencoder as the input. And we'll discuss a little bit more this next lecture, 8.2. The second part, which I also went a little bit quickly last time, and I want to discuss again, was like, there are a lot of cases where you don't have this beautiful pair data, like you have data between maybe an input and an image and an output, but there's many cases where you would like to generate condition maybe on X, you would like to generate Y, but it's great if you have the pair data, like, hey, I would like condition on this, generate this image, but there's maybe cases where I don't have the exact pairing. I have maybe a bunch of painting of a specific artist, and maybe images of the real world, but I don't happen the artist and the exact image of what they were painting. So how do you handle this kind of unpaired data? So you have like X and Y, and so you have like, you would like to be able to condition on X to be able to generate Y, but you don't have the pairing. And the idea here is really cool of cycle GAN. It's really interesting. The idea is that, okay, I want to learn this generator G. That's what I want to learn. I want to learn how, based on X, I want to be able to generate Y. But I don't have, like, to be sure that the Y was done the right way. I don't have that exact pair thing. So what will I do? I will say, hey, what if I had, in fact, two generators? I'm going to learn one that goes from X to Y, but I also want that learn from Y to F. And then my loss could be just like, how well did I regenerate? It's almost, you could say, almost autoencoder, like you encode and you decode. You could imagine a bit, but it's not just any kind of intermediate representation I'm going to learn here. Here, I want to learn one that, in fact, look like something. So for that, I will, in fact, having two losses. And that's the interesting thing, is I will take some image from X, I will generate Y, but in such a way that the Y is able to regenerate. That's kind of the autoencoder. But I will also do it the other way around, where I will take some image from Y, generate an X, and generate back the Y. And by doing that, and by tying the weights so that the G's are the same in both cases and the F are the same, like the same generators and the same weights, then what's really nice, I have two losses. I'm like trying to make them, whatever I created, I synthesize as close to as close as the original. By tying these two together, and by tying these two, I will, in fact, being able to train jointly like both generators. So I will be able to go from X to Y, and I will have got for free also the Y to X if I need that as well. And that was really impressive work that came from that. The results from a photograph, and then because it knows like the style of a specific painter, it was able to switch to this, how Van Gogh, Cézanne, or some other painters will be doing that. And they will, if you have your X and Y, maybe both are images, but some are taken during the summer, some are taken during the winter. Even though you don't have the exact same landscape in winter and the summer, you can swap them around. So that was really interesting. So this is CycleGAN. There's a lot of great things with these architecture, a little bit on the challenge on the optimization, and we'll discuss a little bit more that next lecture. But I want to talk today about probabilistic graphical model to continue the lecture on Bayesian network. And to be able, one thing I wanted to do is like to be able to put that into the context of the whole course. And like we're in week number 8. Where are we in this? Because we had those 5 challenges, and we look at representation. We look at representation, joint representation, and coordinated representations. We were not done with representation. We also look, GAN is also a way to learn representation. And we'll talk next lecture about variational autoencoder. This is a core aspect. If you can represent your data, your multimodal data, efficiently, that take into consideration the complementarity between modalities, this will help. This will help. A second challenge was alignment. I have alignments from different modalities I want to align. We look at all of the attention-based models, the self-attentions, and also look at techniques that look specifically for time series, like dynamic time warping as an example. And we looked last week at extension of that also with the soft dynamic time warping, and we'll look at a few others examples. And then we look at translation models, like, and one example that I particularly like was the module network. So as an example of translation. And as we know, for translation, to be successful in translation, you need to be able to do good representation and good alignment. So translation is really building on top of that. The lecture today and the lecture, like the last 7.2 lectures, was really about fusion. And it's about a step further than representation alignment, and it's about fusion. And it's about doing the prediction, and it's multimodal prediction. And so when we talk about fusion, it can be sometimes a little bit ambiguous and maybe sometimes confusing to compare fusion and representation learning. And I want to both acknowledge and help a little bit in somewhat getting a little bit more detail about the taxonomy that we're using in this class. The fusion is, if you have to look at it from like input and output, representation learning is the idea that I have some input data and I want to learn a way to better represent. And better is on purpose I'm using it in generic sense. It could be better because it is smaller, like more compact. It could be because it summarizes the information. It could be because it emphasizes some aspects like semantic out of it. So this is representation learning. But at the end of the day, in many tasks, you have a prediction to make. A prediction because it's maybe a classification task, it's maybe regression, or could go all the way to generation, but we often will go there with more as a translation task, a translation where you're generating. But in many cases, you're predicting. But what you're predicting, like let's say you're predicting emotions, but you're also predicting maybe, let's say, the personality, or you're predicting like, is it a noun or is it a verb or some aspect of syntax? These predictions also can have some these labels could have some structure in it, and that's where these graphical model, and that's where fusion comes in. It's like when it's time to make that prediction, when does fusion and representation, fusion is closer to the end point, like it's like closer to the final prediction. And it's true that in neural network, for many neural network, it gets ambiguous where the representation ends and where does the final prediction happen. Is the final prediction only the last layer and everything else is about representation learning? It's almost a little bit philosophical. So I will not in this class try to argue where does fusion and representation learning ends and start for neural network. But for some other model, like probabilistic graphical models, there it's a lot more obvious that these are a lot better, or probably better suited for fusion. Because one of the great advantages of probabilistic graphical models is that you can integrate in them a lot of domain knowledge. You can bring domain knowledge that we got from talking to experts or from initial analysis of the problem, or you can also just create a research hypothesis and then test it by testing different graphical models. And so domain knowledge can be done because you have knowledge about the latent substructure. By latent substructure, I mean the labels may be like emotion, like this is what you're trying to predict, but you have knowledge that this label, to be predicting it well, there is some hypothesis, there's some models, experts have studied this process. And as we've seen as an example last week, emotion, if you take the appraisal theory, could be seen, can be formalized with a structure that looks at balance, how you perform and how much effort you put gives you some aspect of balance. And that will also focus how much you focus on the as a person will all come together to finally infer the emotion. And your graphical model allows you to put that domain knowledge. Now, how do I infer learning, performance, and focus? This is where representation learning will come in. And that's why when I'm thinking of graphical models and neural network working together, I think a lot of the graphical models makes more sense on the later part, like closer to the label, because that's where you would like to put the domain knowledge. And for the more high dimensional input data, then let's be data driven and let's just use really good infrastructure that we got in neural architecture to get a better representation. And so graphical model allows you to learn if you have knowledge with what is underneath your emotion, something that's latent. Or there's also domain knowledge between your labels. And so maybe there is knowledge that like certain labels, there's a structure between my label. There's like example here is a temporal structure, meaning my emotion at time t is very likely to be dependent of t-1. This is an example where there is temporal information. And so at that point, graphical model can help. Example of structure prediction. What's called image, some researchers call semantic segmentation. I could predict every pixel by itself, but predicting is this pixel sky, and doing each of them independently does not make sense. It makes a lot more sense to take into consideration my neighbors. Neighboring pixel will, when I predict my label for this pixel or for this pixel, I want to be able to predict it like all together, and I should take into consideration all of those predictions should be coherent together. And so another word we could almost say is like that structure we want to enforce some kind of coherence in my labels. And that's an example in language. It could be from dependency. So if I'm predicting what is maybe the part of speech tags from this or from this word, there may be a dependency between like coherence or dependency in coherence in like predicting them. And so I want to predict in them maybe and take into consideration that structure between the word, that link, that coherence. And that's what the graphical models do so well, or at least allows us to do. And so these are two examples. And so last lecture, we talked about Bayesian networks as a way to be able to model this, like take that domain knowledge and model it. And they're great. And I still love the Bayesian network very much, but they come with a challenge. And when it comes time to take Bayesian networks and on top, bring them with neural networks, optimizing them gets a little bit challenging. And it's part of the reason we don't see as many of them probably working together, although there is some great work pushing the envelope in that direction, but the optimization is always one of the sticking point there. The Markov models nicely and their formulation brings a formulation that streamlines a little bit more the optimization, and bringing neural network with Markov model is a little bit more streamlined. And so I'd like to discuss them this lecture and gives you examples that bring neural networks and Markov models. And to kind of introduce Markov models, I will do a small historical detour, also because one of the first multimodal paper using neural network was in fact using some very similar model to Markov model, and it's a restricted Boltzmann machine. And I said I will revisit it, so I promised that, so I will. So let me revisit the restricted Boltzmann machine as an introduction for the Markov models and the conditional random field specifically as a Markov. But if you remember, and I have 2 or 3 slides just to remind you, the Boltzmann machine was in fact one of the first paper, very close in time with the multimodal autoencoder papers. And there, one of the key aspects of it is that this is a generative model. An autoencoder go from text, go to the intermediate representation all the way. Autoencoder will be go to the text and come back, or the multimodal autoencoder was going to the intermediate and recreating the text or recreating the image. The generative model, what it means, and now you know it because of the last lecture, generative model means that I'm modeling the joint distribution. And so I'm modeling the joint distribution between, in this case, between text and images. And it will be trained also by looking at the joint objective with text and then the hidden representation. And so you will, from a training perspective, we do it layered wise. That's what we hinted at earlier on. Before going into the math of this model, I just want to remind you that one of the advantages of the Boltzmann machine is once you learn it from a generative model perspective, then if I have a joint representation, I can decide to go either way. I can go back to text, or I can go back to images. I can go any way I want, every link. And sometimes you will see it with 2 arrows, or sometimes you will see it with just 1 line with no arrowhead. This is just 2 different ways to present it. And so the multimodal deep Boltzmann machine allowed you to go from image to text, or from text to image. It allowed you to go both ways. And one of the coolest results from this paper was that if you have a task like finding image retrieval, which is primarily often based on the data from the image, but what was really cool here is that the text, by adding the text during training of paired data, adding the text and not just taking the image representation, but using, in fact, the text as part of the how do you embed each image. So how do I embed my image? Instead of just embedding my image with VGGNet, I'm going to embed my image with the Boltzmann machine, which was trained with the text. So it was trained to kind of being a little bit closer to text. And so by doing that, it does improve for image retrieval. But the question is, what are Boltzmann machine, and specifically what's the restricted version? So restricted Boltzmann machine is an undirected graphical model. It is a graphical model. It's a generative rather than discriminative, as I already mentioned. The connections are only defined between the visible and hidden unit. It is not defined between each unit in itself. Like, so within a layer, I don't have connection. There's no structure between them. I don't enforce that. And that's what makes it a restricted Boltzmann machine. I'm about to introduce to you a Boltzmann machine in itself, but the restricted Boltzmann machine is the one that does not have any link between the random variables from the same layer. And the reason people will do restricted Boltzmann machine is that it simplifies inference. That's one of the reasons. Mathematically, the restricted Boltzmann machine, it is an energy model. And I don't know how many of you heard that term before, but if you work with conditional random field, which we're about to talk about in a little bit, these are often sometimes called also energy models. And I'm going to define to you why the term energy models, because some of you may not realize why energy model, why conditional random field is an energy model. It's because it's coming from a lot of these different models like the Boltzmann machine. But the idea of the Boltzmann machine, so you want to model the joint probability. That's what you want to model. That's a generative model. And theta here are your parameters. The parameters are the weight. Let's say you have one weight for each of these link here. And bottom term is going to be just a normalization term. And this is just to say, because it's a probability. But the most important term is the top term. And this one is defining how a specific instance, okay? So x, let's say that x is 0, 0, 1, 1, 1, 0, and h is 1, 1, 0, 0, 0, 1. And let's say that that's my x and that's my h. What I want to know is what the probability of that event to happen. What's the probability that, and because it's joint probability, what's the probability of both having x being 1, 0, 0, 1? I forgot what did I say. And then the other one being 1, 0, 1, 1, 1, 0. What is the probability of both of them occurring? That's what this is really telling me. What is the probability that both of these events happen, these multivariate events happen? And the way to do it is I'm going to compute the potential of these events to happen. And then I will divide by the potential of all possible events. And as you can imagine, because it's discrete, I can do the summation. If these events were represented more like a continuous variable, then I will be needed to integrate. But this equation, what it shows you, it says like this is the potential that the event that I currently have quantified by specific states. How is it that it's likely to happen? What's the probability of it to happen? I just divide by all the events. And an event to happen, how do I know if the event is likely to happen? For that, I will look at all of these links. If you remember, I don't link the the variables within a layer. So there's no link there, but the most important part are the link here between x and h. And so all of these these weights are really going to define how likely. So if the weight is really high between X1 and H1, very high weight, and suddenly, let's say this one is 0 and this one is 1, this is not something I want to see. This is not compatible. This is not a high potential to see this. And so, but if the weight is really low, then I don't mind that these are different, maybe. And so that's what this is going to do. And then there will be a bias terms. But the main one is what's called the interaction term, where we're defining how each of them, and this will be just like a bias, like is X more likely to be 0 or more likely to be 1 kind of bias you could imagine. And so, but the main one is like compatibility between that. And so this is the restricted, but the normal Boltzmann machine doesn't have these restrictions and allows to have any of these to also be linked. And now this, if everything is linked with everything, this is equivalent to this representation. These two are exactly the same. And that's where, like, historically, the Boltzmann machine came first, and then the restricted came after. The Boltzmann machine was like, hey, I have the world, and I observe certain states, X, but certain states, I don't observe them, but I know they exist, but I don't observe them. And I want to know how likely, and then how likely P of X, or maybe if it was one of the thing I want to do, I could go P of X given H, or P of H given X, or I could just go P of X and H. But the idea is that some of them will be observed, and some of them will not be observed. And that's the Boltzmann machine. The Boltzmann machine, and why we call it energy model, is that it comes from statistical mechanics. And you could see it as almost atoms. It was not exactly developed for atoms, but it's like, if this is a very high energy, like thermodynamic, and is it possible to have all of these activated at the same time? And maybe not. If they're all activated at the same time, maybe an explosion will happen or something. So the idea of the Boltzmann machine was that, like, hey, I have I'm going to define between each of my random variables some kind of interaction term, some kind of potential function that, like, how much potential is it that these two co-occur at the same time. And I will use that. And the idea is, like, give me any kind of states, and I will tell you how likely it is that these states exist in the real world. And the core aspect of it was this energy function. And the energy function was like, hey, I have these different states, and how likely is it that these happen? And then it was divided by the Boltzmann constant and the thermodynamic temperature. Now these days, these have been removed. We don't see that in typical conditional random field and all this. But the core of it stayed. This equation is very similar to the previous one. Of X and H, is just that they're just put together instead of having separate observed and non-observed. Originally, everything was observed, or maybe everything is non-observed, but in their case, maybe everything is observed. And so this is the idea. The same idea is that I have some state, I have the potential of this happening, and then I divide by all of the possible other events, and then that gives me a probability. So this is also called Gibbs measure, Boltzmann distribution, or Gibbs measure. That's what this is. This is a very key equation for a lot of models. And we will use that because the Markov random field It's just building from that with a slightly different naming convention, and allows a little bit more flexibility. But the Markov random field is a lot like a Boltzmann machine. The equation is there. We drop the constant. The constant from the Boltzmann machine is not there. But the core idea is the same, is that I have random variable, and my random variables are going to be non-observed, usually a random variable or non-observed, at least not directly. And for each, for this whole link, for all these random variables, I will have this potential function. And this potential function, will be defined by a series of, you could say this mother potential function will be defined with a series of smaller potential functions. And these are all these links, these different links here that I have. Each of them will be defining a potential function. And we'll go into more details in one. But for now, you'll say for each of these links here, I will have one of these potential functions. And it could be just simple. It could be, hey, is it likely that these two events happen together at the same time? And it could be a simple yes or no, like yes, they are very likely when they happen, and I give a very high potential, very high score if they co-occur. Or maybe not, when they co-occur at the same time, this is the opposite. I want them to be in opposite end, and that would be another kind of potential. The algorithm will try to take all of these potential and try to find and maximize, or try to optimize it such a way that you get all of these mini constraints taken care of all at the same time. And so this formulation is often, we call this potential function, and we call this energy function. So you will see both of these terms. So potential is the exponential minus the energy function. And the reason of this naming convention really come from the Boltzmann machine originally. And so this is fully connected. It's very rare that you will see a fully connected Markov random field, although they will see some, and I will show example, and you will usually need to do some approximations to be able to optimize it efficiently. But in many cases, the random field, that graph, that graphical model will in fact have only a subset of the potentials defined. You could call them linked, but the potential. So instead of having all of them connected with each other, you will use some knowledge. I mean, if you have no knowledge, let's connect everything and just wait and hope that I have enough data and I can optimize things. But if I have knowledge, then I can say, hey, there is in fact some information. I know that these latent, or I hypothesize that these latent states will be connected together. In that case, as I mentioned, I will only define my potential over these links. Instead of connecting everything with everything, I will only connect it. And then, so the potential in this case will be like, I have a potential between 1 and 2, and it has its own weight, own parameters. I will define a potential function between 1 and 6, and each of these pairs. This is called Markov random field, and this is the representation that you will have for these potential function. I want to introduce one thing here that's really interesting. Is like, this is, I'm representing here, is like every possible link is pairwise. But what if I wanted, in fact, the potential to be defined between 3 different variables, like maybe H5, H6, and H2. I need to know those 3 random variables to be able to know if this combination is likely, has a high potential of happening. And the typical Markov random field graphical representation, graphical model representation, does not offer that. So using graphical models to represent Markov random field gives some constraint on it, because only you get only these pairwise relationships explicitly represented in a graphical model. And this is why people, and one of my preferred representation is in fact factor graphs. It's another ways to represent the Markov random field. There's the graphical model way and the factor graph. And the factor graph here, if it's only pairwise, it's only, in this case, gonna just add this new factor, which is a square. But the power of it is that you can also start putting factors with maybe some observed variable, because all of this is all my latent variable. But you may also have observed. But the more interesting is this one. Here, I can suddenly connect 3 things together and say, hey, high potential if H5 is 0, H4 is 1, and H3 is 1. Let's say, and or some other combination. Now I have these trinary, if you would like, I'm just creating words, to define over my latent variable. So in the same network, I will have pairwise, I will have triplets, and it can be as complex if you want, although this function will become more complex. And I could also have unary, and the unary will make a lot more sense in a second when I start introducing also observed variables. But let me come back to this one. So this is factor graph. And this is called also what's called a clique factorization. I know it's a lot of terms. I apologize for that. But now when you look at this, there's a clique. And the cliques are, what are the variables together? What is the smallest that I can to compute my potential? And for all of these, it's all pairwise. So that big, the idea of clique is a little bit like when I look at my graphical model and I factorize it. And the clique is this way of factorizing. And so I'm going to factorize by having all of my pairwise potentials. And I will factorize also maybe the unary, and more importantly, like when I have my triplets. So now for this factor here, I can't just use H4 and H3. I need H5, so I need all 3 of them. So my clique to be able to infer that potential is going to be